Now we move on to talk about the components of a mechanical earth model. And those are listed here. So I'm going to give some more insight on each one here. We talked about overburden stress, which is the same thing as vertical stress, and it's shown here. That's in the vertical direction. It's all about the weight of the rock on top of the formation of interest. That's the vertical stress, one of the three principal stresses. The other two are the SH max, which is the maximum horizontal stress, and the minimum horizontal stress. So we have two horizontal stresses, and they act at 90 degrees to one another. So they are orthogonal. That's 90 degrees. Rock strength, that's what I show here. Unconfined compressive strength, right here, UCS. If you apply stresses greater than the UCS, what happens? The rock fails. You develop a fracture. And if you continue to apply stresses on the rock mass on both sides of the fracture, if that rock, if the stress exceeds the frictional strength across that fracture surface, it slips. So the rock actually moves. And when the rock mass moves across the fracture surface, what you have is a fault. And that's the difference between fractures and faults. That discontinuity in the material is the fracture when there is no movement. When the rock mass now moves across the fracture surface, then you have a fault. So you could have this pure material, then it develops a fracture. The material is still intact, but when it actually slips, and I'm going to sketch that, let me clean up this and sketch it right there. When it now slips across that surface, say this is now here, then this is not a fracture, this is a fault, and this is a fracture. And that's the difference between faults and fractures, which is important. The other item I've not talked about so far is pore pressure, and that's basically the pressure of the fluid within the pores of the formation. So it's what you typically call reservoir pressure. And the important thing is it doesn't have to be one value everywhere, right? You could have heterogeneities and you can have higher pressures, and generally pressure increases with depth, right? So in addition to the mechanical properties, we also include typical reservoir flow properties like pore pressure. Some other typical reservoir properties are these components, which is porosity and permeability, because we're not only going to model the mechanical deformation of the rock, we will also model flow of fluids within the rock. So we need the parameters that govern the flow and storage of the fluid in the rock. Permeability governs flow, porosity governs storage. Other components of the mechanical earth model include the elastic properties, which we talked about before. For linear isotropic materials, you only need two elastic properties, any two. You can get any two from any other two. So these are the most common: Young modulus E, Poisson ratio, no. And you could also have K or G, bulk modulus, shear modulus. We're going to talk more about this. If the material is more complicated, so it's not just a simple linear isotropic material. If it is anisotropic, you will need more than just two elastic properties. There are so many of them. You also include failure criteria in your mechanical earth model. And that's basically the criteria above which you will create a fracture in the rock. So once the stresses you apply exceed the when the stresses you apply exceeds the fracture toughness of the rock, for instance, it fails and you develop a fracture, as explained previously.